morning, everybody. Can everybody see me? Everything okay?
Yeah.
Okay, great. All right. Well, announcement. Next Monday will be all virtual and all virtual office hours. I just want to go back to Fayetteville area and see my granddaughters and do some stuff, but I'll be available online as well as virtual for both things. I just have one class, so if you have one class on Monday, you can view me from distance also. And my internet is even better there, so it won't crash. So in any case, it should work out just fine. Basically the schedule for the exams this evening, those of you that are in person who are the athletes, you need to come at 8 o'clock, correct? Okay, so we'll do that same thing. And those of you that came on Sunday, at 7 o'clock last time, please come again at 7 o'clock. And then for those stragglers or whatever else, if others want to come at 7:45 or something, you can move in as people leave. And that should work for everybody regarding the exam. Basically, what I'm going to do today is essentially use another set of slides to go over chapter 4 again with a different perspective and serve as a review. And if you have any questions, please stop me and say, Dr. Douglas, I don't understand that, and I'll show it on the board or something just to explain that kind of concept. So please ask questions, even you who are virtual, okay? So did you all hear that, the virtual people? Is that okay with you folks?
Yes.
Okay, good. All right, thank you. All right, so let's get moving with this. Now, this is a PowerPoint. I will put it on in the shared drive, just in the open area. In our shared drive. It's from a book called Zumdahl, which is a very good textbook too. It has some material that is not in our chapter 4 that's covered later, but I'm not going to cover that on the exam anyway, and we're not going to get to that until electrochemistry and Gen Chem 2. So the other thing is also the schedule has been set up for next semester. Basically for General Chemistry 2, I'm teaching 2 sections. Dr. Gerhardt's teaching 1, and Dr. Powell is teaching 1 section, I believe. So basically, I'll be teaching 2 sections next semester. So that's just to give a heads up for those that want to stay with me as your teacher. What I always liked was having the same teacher for the sequence. And a lot of students do, some students don't, but that's up to you. Okay. So what we're going to do now is go through this, talking about various things, and this will be a different set of slides, but it'll kind of give another feel for where things are. So what I'm going to do now is start it, and I'll start the slideshow for those that can't see it yet. Okay, I'm going to share the screen now. The internet connection should be stable, folks, so keep that in mind. Now, the first thing about in this chapter, it covers water as the common solvent. The key thing about water is it's available, it has ability to dissolve many substances, and that includes ionic materials as well as molecular ones, okay? And essentially you got ionic salts that can be dissolved fairly easily, as are organic materials like sugar, etc. Okay, so essentially if you got sugars, etc., all sorts of other things that go in there. Okay, each molecule is essentially V-shaped with an HO angle of about 105 degrees. They're covalent in nature. In other words, the bonds are formed by the sharing of electrons, and we'll just start discussing that in chapter 6 in the next section. So that'll become a little bit more clear. And it's a polar molecule. In other words, there's a positive region. This is positive, and this is negative. So how will that help to dissolve a salt? Based on what you know of salt, like sodium chloride, how will that dissolve a salt? Can you tell me? How will that help dissolve a salt?
Because salts have a positive and a negative.
Right.
So they can attach the positive and negative for each
Yeah, and kind of drag it away from the thing and kind of break it up, okay? And you can see it for yourself just by dissolving salt and water yourself, okay? And it's kind of obvious what sort of happens at a larger scale, okay? And an example here is just them all coming in next to it and then grabbing off individual ions as things arrange around it, okay? So basically it works pretty well. Now, the concept of hydration, and this has to do with the hydrate lab we did, yes.
How can we tell something is a salt?
Well, usually if it has a metal and a non-metal, that's a salt. Okay, but two non-metals won't be usually, okay? But a metal and a non-metal will. Now, a process by which positive ends of molecules are attached to negatively charged ions vice versa, it causes a salt to split. That's called hydration. That's the lab you did in class, a couple weeks ago, where we made the hydrates, or you analyzed the hydrates or broke the water off, okay? That's hydration. And essentially the water molecule kind of attached to it. Basically, when you dissolve in salts and water, they break into individual cations and anions, just like the previous thing showed. Now, the solubility of ionic substances in waters varies depending on the amount of attraction between ions and basically the amount of things. So what do you think would be easier to dissolve? Sodium chloride or, say, calcium oxide in water? Well, let me put it this way. With you a +1 and a -1 there, and a +2 and a -2 there, what do you think would dissolve a little better in water? Huh? The second one, calcium oxide, okay? Because it has a greater charge density around it, okay? So that'll enable it to break. That's even calcium oxide is reactive with water. That's called lime, okay? But basically limestone is calcium carbonate. Yes.
So how do you know that that one's more soluble than the other one?
Just because there's +2 and -2 associated with it, and so water with the polar nature of it. If you go back, see the polar things, it'll coordinate better around the calcium and the oxide ions.
So a higher charge withdrawal in the water molecule.
Yes. Okay, so, but there's a lot of different ones that dissolve very well. Another example is ammonium nitrate. Like that. This has a lot of negative regions around it, has a lot of positive regions around it, and that dissolves very well in water. Okay, so there's a whole bunch of different examples of those. Polar ionic substances are expectably more soluble in water than non-polar substances. Non-ionic substances such as ethanol are soluble, and the reason they are is because the structure of ethanol, and you'll learn this in organic, looks like this. Oxygen there. With the hydrogen, this was called the Lewis dot structure, which you'll learn later on this semester. But notice these are negative regions there with the positive at this end. So basically this is considered polar also, so that will help dissolve things, okay? It's considered a polar solvent, but that is also there. And you got the polarity of the interaction of the water molecule with the alcohol on the ethanol molecule. Okay, does everybody see that kind of interaction there? And you don't know much about how those work yet, but you'll get the feeling for it later. Okay. Electrical conductivity, the ability of a solution to conduct an electrical current. The solute is the substance being dissolved. The solvent is the dissolving medium. An example is water, or it could be alcohol or some other kind of thing. For example, in this mug I just have hot tea I made yesterday and then heated up today. I made a big pot of green tea, and that's from the stuff that I didn't drink yesterday, but it's just green tea in there now. And that's an example of a solution. An electrolyte is something that dissolves in water to produce conducts electricity. And here's a good example of non-electrolyte. This is a non-electrolyte. Notice the light bulb is off. Here it's weak. So here, this is off. This is lit, and this is in between. So in between, weak. Okay, and that's because some of the ions are not broken off from the other ones. Just like with acetic acid, you have the full molecule there. Strong electrolytes, sodium chloride. Acetic acid is a weak electrolyte. And then non-electrolytes would include sugar. Now, Arrhenius was the guy that came up with the definition of acids and bases, but he also addressed the conductivity properties of solutions. And basically, he was one of the ones that came to figure out that there were ions related to the nature of each of them. And basically, there's a whole bunch of different examples of completely ionized and water stuff, soluble salts, strong acids, strong bases. They dissolve very easily. Salts such as sodium chloride contain an array of cations and anions, disintegrate and undergo. So again, this is a good diagram to kind of illustrate it. The nature of acids. Acids act as strong electrolytes. These break up, and I will put I'll put the PowerPoint on the thing so you can use it to help remind you to read certain portions. And acid is a substance that produces hydrogen ion when it's dissolved in water. Polarity of the water helps produce them. Strong acids break down hydrochloric acid, nitric acid, and sulfuric acid are examples. Strong bases, potassium hydroxide is an example there. So a whole bunch of different examples. And then weak electrolytes, that would include vinegar, citric acid, other things like that. And believe it or not, there are a lot of weak electrolytes that are used for flavorings. Ascorbic acid is vitamin C. Citric acid is the tangy as well as ascorbic acid is tangy, but citric acid is the tangy in lemon and orange juice. Weak acids, this is acetic acid, is just a partial dissociation, and essentially you can get the smell there. Weak bases would include ammonia. That's one reason you can smell ammonia if it's dissolved in water. You open up a bottle that has ammonia in it, you can smell it. That's because it's considered a weak base, okay? It still remains as this one molecule in solution. Non-electrolytes, example would be ethanol and sugar. If you put them in water, they won't conduct electricity. Now, compositions of solutions. Chemical reactions in solutions occur when two solutions are mixed. To perform the stoichiometric calculations, one must know the nature of the reaction, the amount of chemicals present. And that essentially, solving these kind of problems enables setting up the reaction first and then balancing both sides, just as you did with the other ones in chapter 3. Molarity is the commonly used expression for concentration expressed as moles of solute per volume. Now, if you remember in chapter 3, we went from grams to moles to grams. And all this does now is you have grams per liter. And because you want to be in moles, you have moles per liter, okay? And moles per liter here, and the amount of grams is based on the volume of the liquid added, of liquid. So essentially the volume of the liquid added there is the most important one. And so essentially you modify the volume, you add less chemical to it or more. Yes?
When doing stoichiometry, is it possible to switch the moles to liters? Can you have liters?
Well, yeah, sometimes if you're doing the conversion,
Okay.
and because again, if you have like 2 moles per liter and 2 moles of sodium chloride per liter of solution, sometimes you will use that to kind of in the relationship between one side or the other for the reaction, and just like you would in the stoichiometry you did in chapter 3.
So you, in that situation, you can put moles on the bottom and find liters.
Yes, and basically you're just making conversions, because that's the same thing as saying 2 moles of sodium chloride are in that 1 liter of solution. Okay? Calculate the molarity of a solution in which 146 milligrams is dissolved in enough water to make 500 milliliters. Okay, what's the first step with this? No, even before that. You're right, that's step 2. But even before that, what's the first step? Huh? Yeah, calculate the moles. So you want to get the molar mass of potassium chromate. How would you determine that? Yeah. Brandon, how would you determine that? The molar mass of potassium dichromate. Yes, that's correct. Okay, good, very good. Okay, so then you just do the conversion. Now I'm not going to bother with my art, so let's do that first. Okay, that's the answer, but I guess they're not giving it to you. So let's go through the process. 184.6 milligrams. So what would be the first thing we could do? Convert to grams. Very good. So essentially you have 1,000 milligrams equals 1 gram. Okay. So milligrams cancel. Okay. And now you use the molar mass of potassium chromate. Well, let's look at it. 39.1 times 2 is 78.2. Chromium is 52, so it's 2 of them, so that's 104. And then 7 times oxygen, which is 16, so 5 times 16 is 80, and then 2 more would be 32, so it's 112. So you have 112, we'll just add this up. What is it? 294.2 grams. So essentially you have 294.2 grams of that per 1 mole of it. So the grams cancel. Now you have moles. Okay, so now what do you do there? Well, you want moles per liter, right? So essentially here, you had 500 milliliters of solution. So then you use a new thing of 1,000 milliliters equals 1 liter. Okay, so cancel things. Okay, you have milliliters cancel, liters, moles per liter, grams cancel, and just do the math. Yes, 1,000 milliliters is 1 liter. Yes. So you just convert it, and that's the final answer. And basically the answer ends up being 1.255 times 10 to the minus 3 molar. Okay, that's the answer. Now, I know each of you could do each individual step. You've been learning that all along. So what I'd like you to do on the exam, if you see a problem like this, it won't, I promise it won't be that complicated. I'll try and keep it simple to teach you the concept. But the point is, there may be something like this. So set it up properly, go one little step at a time, and you'll do just fine. Okay? That's the whole point of doing the homework. Do any of you virtual have any questions?
No.
Okay, very good. All right, let's go to the next one. Calculate the molarity of a solution prepared by 1.56 grams of HCl in enough water to make 26.8 milliliters of solution. How would you do that? Yeah, grams to moles, and then put it in liters again, just like before. So let's do that. We have 1.56 grams of HCl. HCl is 36.45 grams of HCl is 1 mole of HCl. Okay, grams of HCl cancel. You end up there with then the next step, 26.8 milliliters. Well, you got to convert that to liters now. 1,000 milliliters equals 1 liter. Okay, so milliliters cancel. What's the number? Well, we calculate it out. Where are you going to find the molarity? What do you know? You have the mass there, the amount of solution. What information do you need? The moles of the solute. So set that up first. How do you get there? What are the number of moles of that? Well, that's the moles of the solute. Okay. What is the volume of the solution in liters? Well, that's the amount of liters. Well, then you just take this number and divide it by 2.68 times 10 to the minus 2 liters. That gives you your answer. Now, why did I put it in this form? Why did I put it in that form? Yes, to follow it along. So that's why I encourage you to do the same thing. Yes.
With conversion factors, can you just have a blank at the top?
Mm-hmm.
As long as it cancels, it's just one.
Yeah, because you're at, the problem says you're making 26.8 milliliters of solution. Okay, so that's it goes on the bottom because it's per milliliter, and then you convert to liters. Yes.
If it says milliliters, do we have to convert it to liters?
Well, it depends. In what you did in the lab last week, because milliliters were both sides of the equation, the 10 milliliters of acid and then the 34.3 milliliters of base, the milliliters are the top and the bottom, they canceled out. Okay, and we'll get to an example like that later. But if you have it in milliliters and you're trying to get molarity, which is moles per liter, then yes, you have to. Okay. It's always you have to. You want to get into units that you want the answer to be in. What is the molarity of the solution there? Well, that's your final answer. The units are correct for molarity. Yeah. That's the last thing, but I recommend you use the slide that I did earlier. And what I'd recommend for those of you studying this afternoon to prepare for your exam, work some more problems like this, because there will be some stuff on the things. Okay. Calculate the number of moles of chloride ions in 1.75 liters of that molarity thing. Now, how hard is that? Yeah. So essentially you have this 1.0 times 10 to the third minus 3 moles per liter. Write it out so you have them. You change the big thing to M. And how many liters do you have? How many liters do you have? Yeah, 1.75 liters. Okay, and that's how many liters you have. So the liters cancel. And then for every 1 mole of zinc chloride, how many moles of chlorine are there? No. For every mole of zinc chloride, how many moles of chloride ion are there? 2. Yeah, very good. So you put 2 moles of chloride. There you go. And just do the math. Well, because you're told that it's 1.75 liters of thing. You're converting it to moles first. See, this is the answer there, okay? That's part of the problem. You have a certain amount of moles, you convert it moles per liter, you're converting it to liter to moles to find out exactly how much is in that much solution, okay? Well, because there's nothing on the bottom, that's part of the problem. You're just multiplying it out because essentially you have moles per liter, molarity times the volume, okay? That equals the number of moles. Okay, this is moles per liter, right? This is liters. So liters cancel. Okay, that's where it comes from. Yes. Well, zinc chloride, when you dissolve it, what happens to it? Well, you have zinc plus 2 aqueous plus 2 chlorides aqueous. Okay, I skipped that step. That's the ionization of it. Yes.
So I'm kind of confused. Right, so we're doing, you have the molarity and you're
Yeah, the molarity is in moles per liter. So I'd recommend you write out moles per liter with it. That's also for analyzing the lab that you did last week or the week before. The lab reports are due this week and thing before your exam. Okay, but this will help prepare you for the exam too.
molarity is equal to moles divided by liters. So if you have molarity, so you're multiplying molarity by the liters to get the moles.
Yeah, molarity times the liters to get the moles, right?
Yeah, but how
We'll say we have a 1 molar solution of salt water, okay? You want to know how much salt is in it, how many moles of salt is in it. You have 2 liters of it, 1 molar solution of salt water. Okay, so let's say we have a 1 molar solution of sodium chloride. Okay, 1 molar. That's moles per liter, right? So you have 2 liters of it. So how many moles of sodium chloride are in there? 2.
No, but what I was asking was how are you just getting the moles of chlorine out of the zinc chloride?
Well, from the equation, zinc chloride, as it ionizes, it forms zinc plus 2 chlorides. That's where it comes from. This is the 2, just in the stoichiometry that you learned in chapter 3. That's the ionic equation. That's how the ionic equation is used. Okay?
So we really should have just written the equation out and balanced it and then done it.
Yeah, you can do that. I just skipped that little step because I hope that you were able to run up a little, okay? And think that through yourself. But that's the purpose I let you ask questions, okay? So essentially we could have done it. Zinc chloride goes to zinc plus 2 chlorines. But as you get the hang of it, you won't need to do that all the time. You can just see it for yourself. And believe it or not, that's why doing homework problems as many as you can will help you learn this stuff. Okay, it's not really about memorizing it. It's about just going through the steps for yourself, learning how to walk. Okay, where are you going? Well, first you have that. You have the molarity and the things. What information do I need to find the moles of chloride? You balance the equation for dissolving it. How do you get there? What's the balanced equation? That's essentially what we showed. Okay? You start with this one. What's the molarity of the chloride ion? Well, you have 2 liters. This is liters. This is moles per liter. Okay? So this ends up being 2 moles of, so you have 2 liters. Oh, sorry. So that's the number of, that's the molarity. That's the concentration, molarity of the concentration. So it's 2 times that. So I'm sorry, I went ahead of myself. But this is now 2 molar in chloride ion. They did a slightly different way than I would have, okay? Because you can see that the 2 is there. So it's almost intuitive how those do. But they added the extra step in there that you may not need to do yourself. If it's helpful for you to do it, by all means do that. How many moles of chloride? Well, basically you set up the problem same way there, 1.75 liters of solution, and then you have the moles of chloride thing. The only thing I did was I put that last step in at the end, where if I go back to show you my diagram, right here, see I have 2 moles of chloride over 1 mole of the zinc chloride there. I put it at the last step. I just like to do it that way. Okay, if you want to do it that way, that's fine. If you want to do it the way they do it, by all means, give it a shot. Okay. I will go back and then delete this part just so it's not confusing there. Typical blood serum is about 0.14 molar sodium chloride. Okay. What is the volume that, what volume of blood contains 1 microgram of sodium chloride? Another example, where are you going? Milligram, I mean. Well, you have the molarity of the sodium chloride, 1 milligram of it. What do you need to determine it? And then how do you get there? Well, convert the number of moles. First, you start with 1 milligram. You convert it to grams, and then you go to moles. So that essentially is what I would have done for you too. But again, I don't want to mark it up if it's already done for you. But again, if you draw the line that way and do it that way, one step at a time, you'll follow the logic a little better. But again, you convert the number of milligrams to grams, then get at the number of moles of that. That gives you the amount there. And then you can determine how many grams there are there, what volume contains 1 milligram there. It's called a V. So you have V times the molarity. That'll be the, to get 1.75, you calculate what that V is. So you solve for volume by doing the division. And so basically you have 0.12 milliliters of blood contains that much sodium chloride. Now, a standard solution is a solution in which concentration is accurately known. Essentially, it's weighing the substance and then dissolving it and doing it in the flask. And that was shown on a previous slide earlier as well. Okay. To analyze the alcohol content of a certain wine, they use potassium dichromate. How much solid sodium dichromate must be weighed out to make that solution? Well, you want in a liter, you want 0.2 moles. So this is moles per liter. So you convert it to get that amount of moles. So where are you going? You want to calculate the mass. You want to have 1 liter of that solution. What information do you need to find the mass? The moles of that required. How do you get there? And then it shows 1 liter solution, 0.2 moles. So you need 0.2 moles of it. Then you convert it to grams there by using the molar mass. And that's the amount you would weigh into a thing and then add to the water. Weigh and add to water to get that solution of you want, okay? Dilution is the thing to get, since only water is added, the number of moles before equals the number of moles after. So essentially you have the M1V1 equals M2V2. Same thing, this is dilution. So that's the same formula used with this as you would with neutralization that you did last week, where at the equivalence point, H plus would be the concentration of OH minus on the other side. So essentially you have there H plus equals OH minus, the amounts on each. So there, that's a molarity of 1 times the volume of 1 equals the molarity acid, molarity of the base times the volume of the base. And that's essentially what you did last week. And dilution is the same thing. Yes?
Is that formula only used for solutions?
No, I just showed you it's with the acids, like here, acids and bases, neutralization, because it's all about the moles on one side. The moles on one side equals the moles on the other. With dilution, you say you weigh out a mole of sodium chloride and you have it. You add it to 1 liter of water. Then you add another liter of water. Does it change the amount of moles in it? No, no. All you're doing is adding more water to it.
So is it only if you're dealing with a certain compound?
Well, you could do it with anything, but what I'm saying is moles equals moles with just dilution, because you're not taking it out or adding any salt to it. You're just adding water to it, which is Irrelevant. It doesn't change the amount of moles that are already in there. They don't magically disappear or react with something.
Okay, so is it only in neutralization?
Yeah, because basically with the neutralization, we'll talk about that in a minute. Basically, the neutralization is you have the moles of hydroxide at the equivalent point equal the moles of the acid. That's the point it goes from clear to pink.
This is a one-to-one ratio.
Yes. Okay. And again, dilution, the ultimate method there, and these are some examples. And I recommend you go through them yourself with the same process. Okay, and then essentially there's a couple examples there related to it. Now, types of solution reactions, and basically what we talked about in our chapter were precipitation reactions and acid bases. Oxidation reduction is in this chapter. I really love teaching it. My students get it fairly thing, but our book doesn't use it, gets to it in electrochemistry, which is in Gen Chem 2, which is fine. So basically, all I want you to do is worry about to prepare for today's exam is just use the first part of this chapter, and I'll talk about each of those related to it. So when two,
Reduction reactions are on the test.
no, not because it's not in our book in chapter 4. I didn't pick the book, but these slides are from a book that does have it in there. It's like half and half. Yes.
So we won't be calculating oxidation numbers or anything like that?
Well, that will be, but not oxidation reduction, balancing oxidation reductions. I really like teaching it, and my students get the hang of it because it's the half reaction method that I kind of introduced a little, and then you add to that, and then have the amount of electrons equal on both sides. That just adds some more steps, but it's better covered in electrochemistry. Okay. Someone else have a question over there? Okay, so let's look at each. When two solutions are mixed, it precipitates, separates the solution. It's an insoluble example. So one obvious example is sodium nitrate, AQ plus sodium chloride, silver nitrate, sorry, gives silver chloride solid plus sodium nitrate aqueous, AQ. Well, just by the you do the experiment, it comes out solid.
Is that based on solubility?
It's based on the solubility rules, but based on experiment. You just mix the two clear solutions and you get a solid.
Let's say like we're taking the Ionic equation. I know you don't take the you don't break apart something that's a solid liquid or gas.
Well, in this form, with a precipitation reaction, this is AB plus CD goes to AD plus CB. And when you have a precipitation reaction, the AD is the precipitate. That's how it works with the precipitation reaction. Always.
Yeah, but on the test, I don't think you're gonna say like this is a precipitation reaction. I think we're gonna have to know that it is. And
So that's why you work practice problems, and that's why I'm teaching this to you.
No, I understand that. I just don't understand how you can spot if something is insoluble or not.
Well, by doing the experiments, which they already did, in which the book describes it, and you read it and you work the little problems you get a practice for. The heavy metals like silver and other things are normally given soluble compounds. That's that little chart. There's a chart about the insoluble parts, the solubility rules.
Are you gonna give us that chart?
No, it won't be necessary. I just want you to use some logic based on using it.
So we should put it on our note.
Yeah, if you like. Yeah, that's fine. But it won't be necessary if you understand the nature of precipitation reaction. I'm not going to throw an AB thing that doesn't give a precipitate. Okay, like for example, I could give you this: potassium nitrate plus sodium chloride. Well, how would that break down? Well, that would end up being potassium chloride plus sodium nitrate. Am I going to use that on an exam? No. The reason not is because they're all soluble. There's no precipitate on the other side. It's just you're mixing the ions. They're all soluble because the rules say sodium and potassium salts are all soluble, so they're all soluble. That's known as a trick equations. I hate them. Okay, I don't want to frustrate students by putting tricky questions in there. Standardized exams will, but that's their style. That's not mine. I don't believe in frustrating students. Okay, particularly biology students that learn differently. I hated tricky questions myself, so I don't use them myself. I try not to. But if you see an A, B plus C, D, whatever, it's going to be a neutralization reaction, which gives water, which is the same thing as a precipitate. Okay? An example there, that this is the solid that comes out. See the thing on the right? That's an experiment. That answers your question. That yellow powder, that comes out. They do this by experiment.
So will that be like, we have a picture of that on our test?
No,
Well, then how do we know?
because you follow your logic and to think about why is Dr. Douglas putting it on there as an example.
I don't know what the
Well, that's why you do homework problems. Yes. And practice the problems, okay? You'll get the hang of it. You'll get to understand it. And when I promise you, and I'm not going to give tricky questions, then look, my job as your teacher is not to when you're taking a test put my foot out so you trip on the exam. That's stupid. Here, this solubility chart. If you want to sign it, you can put that on your card if you want. But if you work enough problems, you won't need it. That's the whole point. They're valuable to a point, okay? Now, see, using the solubility tables, Brandon, these are the kind of problems. Using the soluble tables, what's going to happen when those two solutions are mixed?
There's going to be a solid.
Yes, and what is the solid main thing going to be? Is it going to be the potassium or is it going to be the brom? Is it going to be the barium?
Potassium chloride. That's AD. You said it's always AD. Did you know?
Well, if you have barium chloride, that's the A. Plus potassium nitrate, that's the A. But barium, if you look at where it is on the periodic table, it's down. It's a big atom. So the big atoms in the metals, they're going to always form precipitates. Okay. So basically, you have these things here. You set up the equation, dissolving the solid in there. Since they're all things, essentially you have the different things, the possible solid products. The possible products could be potassium chloride or barium nitrate or barium chloride. Okay, you look at these things to see if they're soluble. No precipitate forms when they're mixed. Why? Well, because this is a nitrate and this is a chlorine. This is precisely why I don't use these examples on the exam. So there's not going to be precipitate. But if you look at the previous one, what was it? This was potassium chromate and barium nitrate, not potassium chloride. Okay? So again, this is the way they would confuse students by putting this there in there because you confuse both of them. Okay, but now if we go to the next one, complete ionic equations, net ionic equations here, then we have here, this is an acid-base reaction, the complete ionic equation that you get, the net ionic equation. This is a solid, the ferric hydroxide, and then go through these steps. And then the precipitation reactions, the stoichiometry work there too. And you can give different examples of that. Which one is limiting, etc. with that as well. And then acid-base reactions, where you have these two there. You want to find out where it's complete. This is what was addressed in our lab last week, where this equals this one. So again, you use M1 V1, V1 equals M2 V2. And what I'd recommend you do in the precipitation section of our book, practice those stoichiometry questions yourself. Hopefully you've been doing it all along. And then basically there, how much of reactants are both in there, which one is limiting, etc. And then the titration, that's what you did also. So to help prepare you for the lab exam, I do recommend you go through this as well, okay? Okay, titration of acid with a base, and you get the pink, just like you did last week.
And is this already posted on the Google Drive? Or-
Yes. And then oxidation reduction, and we're not doing that, okay? Yes. Sorry?
The lab quizzes, are they due today?
No, they were just recommended 1 through 5 by today to have them finished. They're due at the end of the semester, but some people are already turning them in, which is just fine. But you don't have to turn them in. But what my point is that to get people so they don't do them all at the last minute, the whole point was to have them done. There will be some questions on the second exam on the lab quizzes. Okay? Any questions? Yes.
The lab safety video stuff, is that on the lab exam?
No.
No.
No, it will be for the second exam, not the first one, because
The first one doesn't have any of the safety stuff.
Dr. Gerhardt gave a recommendation for 1 through 5 to be done by October 5th. I agree with him. That's all. It's just so you pace yourself through the semester. Okay? Okay, we're all done. Thank you very much, everybody.